In our final section of Unit 7, we will explore derivatives of inverse functions. So let's remind ourselves about what we know about inverse functions. So you may recall a couple of things from Algebra 2. The composition of inverse functions always results in x. We'll come back to that in a second. If the ordered pair a comma b is on the graph of f, then b comma a is on the graph of the inverse of f. And lastly, the graphs of inverse functions are reflections of one another over the line y equals x. So please don't skip ahead for this part, but I'm just gonna come back to a function we know, or we've worked with a lot this year, f of x. And I'm choosing this because I think you already know the inverse of f of x. But if you forget, something you may have learned in Algebra 2 is that, I'm going to call this y for a second. If I have y equals the natural log of x, if I want to find the inverse, I can switch x and y. So I'm going to write x equals the natural log of y, and then I can solve my new equation to isolate y. So if I want to get y by itself, I would need to exponentiate both sides of my equation, which on the right-hand side will give me just y, and I get e to the x equals y. So I could conclude that the inverse of f is e to the x. And I chose that because we've worked with natural log and the natural exponential function very often this year. So let's look at the graphs of ln of x and e to the x. So I made this graph in Desmos. The green line is y equals x. The red curve is our logarithmic, our natural log, and the blue curve is our exponential, e to the x. So you may also recall from Algebra 2 that really every exponential, unless it is transformed, so unless it is stretched or shifted left or right, it doesn't matter the base. Every exponential has this ordered pair 0, 1 on its parent function. And similarly, every log, regardless of the base, has this ordered pair 1, 0. So this comes back to that property that if a comma b is an ordered pair on the graph of f, that b comma a is an ordered pair on the graph of its inverse. Now we could generalize that for all of the ordered pairs. Finally, you may remember from geometry, if you were in a geometry class where you did diagonal reflections, that to reflect in geometry, if you have an ordered pair x comma y, if you want to reflect that over the line y equals x, you just literally swap. You just switch them. Okay, so lots of ways that we can rebuild our knowledge of inverse functions. So I want to go back to that property about them being compositions of each other. So if you recall what that means that f composed of its inverse of x should yield x. So in this case, the natural log composed of e to the x is in fact x. And for these two functions to be inverses, it must be true either way. So if instead I compose the inverse function of f with f, I now get e to the power of the natural log of x is x. Okay, so we are relying heavily on some Algebra 2 knowledge here. Just to look at one more example, because this is going to come back to what we're talking about. Let's look at a much easier one. Let's just look at lines. So again, the green line is y equals x, but the red line is f equals 2x, and the inverse of that would be f, or the inverse of f equals 1/2 x. So again, we could just swap our x and y and solve for y. So what I want to point out here are the slopes. So if I look at my red graph of f, the slope is 2, and I may notice that the inverse function, the slope is the reciprocal of 2. So let's not confuse this one when we have perpendicular lines. You may recall from geometry that perpendicular lines have opposite slopes that are reciprocals, so like 2 and -1/2. But I noticed that these lines that are reflections of one another could not possibly be perpendicular, except for in the event that one is horizontal and one is vertical. Okay, so let's go back to what we're talking about on page 104. So if we compose f with its inverse function, so the inverse of f, we said already that we get x, and in this example, we can take the derivative of both sides to once again derive the formula for the derivative of an inverse function. So we've got to apply the chain rule here since we have a composition of functions. So in the second step, we are just showing in this line that we're going to take the derivative of both sides of this equation with respect to x. And then in this third step, we are applying the chain rule. So the derivative of the outer function, which is f prime, keep the junk on the inside, times the derivative of the junk. This is how you would notate the derivative of the inverse of f of x. And then all of that is just going to equal dx on the right-hand side, which is just 1. And then lastly, if our goal is to isolate the derivative of our inverse function, we are just going to divide on both sides of our equation. So we get this last line by dividing by f prime of the inverse of f of x on both sides, and that ends up here. Oh, it's going to be a mouthful to say that. So if we know that point A comma B lies on the graph of f, that means that B comma A lies on the inverse of f. So to find the derivative of the inverse function at B, we could plug in what we know to the above formula, or what says above, but then it's in the box below. I suppose it's in 2 places. So if f of A is B, and we know that the inverse of f is in fact the inverse function of f, I'm not really sure how we would read that, how else we would read that, then the inverse of f prime, so the derivative of the inverse function f of B is 1 over f prime of A. All right, so in other words, if we're finding the derivative at x equals b, we are just finding the reciprocal of the derivative of f at x equals a. So going back to that linear example, now this one's easy because we don't really have to evaluate the derivative for different values of x because they're lines. So for my red line, I don't need to pick a particular value because my derivative is always 2 since that's linear. But again, I notice that the derivative of the inverse function is the reciprocal 1/2. When we're working with curves, and we typically are, then we're going to see something like this. So we'll see the symmetry here. Again, the derivative of the function f at some particular point a comma b, well, if I swap a and b and I consider b comma a, the slope of that tangent line there is the reciprocal. Okay, so let's try some of these examples on page 105. All right, in the first example, we're given that f of 1 is 3. So if it's helpful, I could think of a comma b is the ordered pair 1 comma 3. So then I'm also given a value for f prime of 1. So I could think of that as my f prime of a. And I'm asked to evaluate the derivative of the inverse function of f at 3. So remember, for this inverse function, b comma a, or in this case 3 comma 1, is a point on the inverse function of f. So using that formula from page 104, I know that if I want to evaluate the derivative of the inverse of f at some value b, that's going to be the reciprocal, so 1 over the derivative of f, so f prime at a. So if I just kind of fill in what I got here, my inverse of f, its derivative at 3, is going to be 1 over f prime of a, which is f prime of 1. So it is relevant that we are told that f prime of 1 is negative 2. So 1 over negative 2 is just negative 1/2. In the second example, we're given a function f, and we're told specifically x is greater than 1, and we're told that g is the inverse function of f. So we know that g would be the same as the inverse function of f. And we're asked to evaluate g prime of 6. So if we are to do that, given f, what we want to remember is that this g prime of 6, that is an x value for our function g or g prime. We need to remember that is a y value of our function f. So we don't want f of 6. Rather, we want to know for which values of x that are greater than or equal to 1 is f equal to 6. So we should set f equal to 6. From there, since we have a quadratic equation, we should probably get that equal to 0. So we get 0 equals x squared minus 2x minus 8. Then we could probably go ahead and hopefully that is factorable. Let's see. What multiplies to negative 8 has a sum of negative 2. How about x minus 4 and x plus 2? Does that work? Yes, it does. All right, so lastly, if we were to use the zero product property to solve that, I would get that x equals negative 2 and x equals positive 4. And since we're given the condition that x must be greater than or equal to 1, we are just going to use the positive solution of 4. Okay, so now we know that for the graph of f, that when f is 4, we get 6. Therefore, I could think of this ordered pair 4, 6 like my a, b. And I know on my function that is the inverse that g of 6 is going to give me 4, for example. All right, so we now know the x value for which f of x is 6. But if I recall, if I'm trying to evaluate g prime of 6, I really need to know not f of 4, rather f prime of 4. So if I want to find g prime of 6, that's going to be the reciprocal of f prime of 4. So again, just using that formula that we derived on the previous page. Well, we can find f prime, no problem. So f prime of x would just be 2x minus 2. So now if we evaluate this function for when x is 4, I get 2 times 4 minus 2, 8 minus 2, which is also 6. Wow, okay. You can tell I worked this example out recently. Just kidding. All right, so g prime of 6 is 1 over f prime of 4. So, therefore, g prime of 6 is 1/6. All right, let's check out this final example. It looks like a great FRQ exemplar. So let f be a continuous function, and we're given selected values of both f and f prime in the table. So part A, we're just finding the equation of the line tangent to f at x equals 2. So recall that if we're using our point slope form of the line, y minus y1 equals m times the difference x minus x1. That is the same as y minus f of a equals m. Nope, instead of m in this notation, we'd say f prime of a times x minus a. Okay, whichever notation you prefer. Potato, potato. Find the equation of the line. So we need f of 2, which we are given in the table is 4, and f prime of 2, which we are told in the table is 3. So if I'm writing my equation of that tangent line, 2 comma 4 is my point of tangency, 3 is my slope, thus y minus 4 equals 3 times the difference x minus 2. In part B, we're asked to approximate the value of f when x equals 2.1. So that's pretty straightforward. We just plug that in. So y minus 4 is 3 times 2.1 minus 2. So I could rewrite that y equals 3 times 1/10 plus 4. And so we get, what, about 4.3 when we add that up. So remember to communicate clearly what we just found. So I would somewhere show that that is our approximation of f of 2.1. All right, part C, we're asked to find the average rate of change of f prime on the interval of 1 to 4. So since we're finding the average rate of change of f prime, that's going to be f prime of 4 minus f prime of 1 over 4 minus 1. So again, just using our table, f prime of 4 is 4, f prime of 1 is negative 2, all of that over 4 minus 1, which is 3, and we get, what, 6/3, which is equal to 2. All right, part D, use a left-hand Riemann sum with 3 subintervals in the table to approximate the definite integral of f from 1 to 4. So when we have 3 subintervals, either in the table or as indicated as by the data, sometimes it's worded like that, we just want to look from where x equals 1 to where x equals 4 and make those 3 rectangles. So up in my table, from 1 to 2 is our first rectangle, 2 to 3, 3 to 4, and in this example, delta x is constant. It's 1 every time, but we know when we're working with the table in a Riemann sum, we got to be careful there. All right, so since we're doing a left-hand Riemann sum, that means I want the left-hand value of each rectangle. So for when x is 1, that's going to be f of 1. I don't know why I circled the derivative as well. When x is 2, that's f of 2. When x is 3, that's f of 3. Okay, so for our left-hand Riemann sum, from 1 to 4 of f of x, don't forget dx. It's not ornamental. It is, in fact, our differential. That's going to be approximately equal to f of 1 times our delta x of 1 plus f of 2 times our delta x of 2 plus f of 3 times our delta x of 3, which is just 1. So since we have this like really big test coming up in May that determines whether or not we earn college credit for this class, let me just remind you that anytime we are showing our work for a Riemann sum, we must show a product and a sum, or in the case of a trapezoidal, it should look like a trapezoid. Well, the area formula, it shouldn't actually look like a trapezoid. Okay, so our approximation is about 7. All right, part E, we're now told that g is the inverse function of f. I could write that as g equals f to the -1 power. We often use that like with sine, cosine, tangent to show an inverse. So if g is the inverse function of f and we're asked to evaluate g prime of 1, this is where we have to remember that if 1 is an x value for g, it is a y value for f. So remember that if f and g are inverse functions, if a comma b is on our function f, then b comma a is on our function g. So I think the mistake that I'm tempted to make here is to look in the table for where x is equal to 1, but we really want to look in our table for where we have an output of 1, not an input. So sometimes it helps me to kind of write this out first. If I'm finding g prime of 1, I do need to know f of what value gives me 1. So again, in my table, if I look in my row for f where I see a 1, that happens in our table at f of 3. So I know that 3, 1 is a point on the function f, thus 1, 3 is a point on its inverse function g. So lastly, if I'm finding the derivative of g for where x equals 1, that's going to be 1 over, or the reciprocal of the derivative of f at 3. Not at 1, but at 3. So f prime of 3 is -1. So we get 1 over -1, which is just -1. Okay, lastly, man, this is a throwback FRQ. Last question, use the data in the table to approximate the derivative of f at 2.5. So I know that if I'm estimating a derivative, I'm estimating an instantaneous rate of change using an average rate of change. So I just look in my table, what's the closest, tightest interval around 2.5? And in our table, that's going to be between x equals 2 and x equals 3. So I'm going to use the average rate of change of f over that interval to approximate its instantaneous rate of change. So again, in a free response question, it's necessary to communicate what I'm doing. So let's write f prime of 2.5 is approximately equal to, and then I'm going to have f of 3 minus f of 2 over 3 minus 2. And I already forgot from my table. Let's see. F of 3 is 1, f of 2 is 4. So 3 minus 1 over 3. Oh, did I do that in the wrong order? Yep, sure did. Try that again. F of 3 is 1. F of 2 is 4. 1 minus 4 over 3 minus 2. That is what? -3 over 1. -3. All right, that's all we've got for Unit 7, Transcendental Functions. Good luck.